Now, the last thing that I want to talk about is this creature called angular momentum, and this sounds a lot like linear momentum, and it has a lot of similarities. Essentially, if you have an object that is rotating, it has some inertia, and angular momentum is just going to be inertia of rotation, if you will. Now, if you think about having linear momentum, which was mass times velocity, instead if you have an object right here and it's moving, then it tended to like to stay moving, so it had momentum. If you have an object that is rotating now, then it tends to want to stay rotating. So we have this thing called angular momentum, and linear momentum was defined to be mass times velocity. Angular momentum is just going to be rotational mass or rotational inertia multiplied by angular velocity. Now, in kind of shorthand, we know that rotational inertia is the symbol I, and we know that angular momentum is, or angular velocity is the symbol omega. So angular momentum is just going to be I times omega. Now, what angular momentum boils down to is pretty much the same as linear momentum. If you had an object and it had no linear momentum and you wanted to get it moving, then you had to apply a force. If you have an object that's not rotating and you want to get it rotating, then you're going to need to apply a force, and not just any force, but a rotational force, also called a torque. So torques are going to change the angular momentum of an object, and we can just kind of restate Newton's first law for rotation. An object is going to stay rotating unless it's acted upon by an external net torque. And angular momentum is going to be one of these quantities that are conserved, and what that means is as long as there's no external net torques, then the angular momentum of a system is going to remain constant. So we can say the rotational mass multiplied by the rotational speed has got to be equal to a constant. And if we had scenarios where we could change the rotational mass, then the angular momentum has to go up or down correspondingly. So if this guy goes up, then this guy's got to go down. The product of those two has got to be a constant. And this looks a lot like linear momentum, where as long as we didn't have an external net force, then the linear momentum was going to be a conserved quantity, or a constant. Now, applications of the conservation of angular momentum is if you think about a freestyle diver who starts rotating, then whether he pulls his arms in or out, he's going to rotate faster or slower. Or you can think about a figure skater, where if a figure skater goes ahead and they puts their body out like that and they get themselves rotating, and then they tuck themselves into a nice tight little tight object, then they're going to tend to rotate faster. Kind of an application on this, and I have a video of this, of me doing this, is if you have an object, a professor like this, who is not a dumbbell, by the way, and he has a big rotational mass, then his rotational mass times his angular speed has got to be a constant. So right here he's got a large rotational mass and a not so large rotational speed. But as he brings these guys inwards, remember that rotational mass depends on mass as well as distance, his rotational mass goes down, and so his angular speed has got to go up. So maybe to put some numbers on this, suppose you had a rotational mass of 10 and an angular speed of 1, then 10 times 1 has got to be equal to 10. Now right over here, his rotational mass, perhaps it went down to be 1, then his angular speed had to go up to 10. So the product of these two have got to be equal to 10. So here we have 1 and 10. Just to kind of finish it off, suppose by pulling the weights inward, the rotational inertia of this man reduces itself to half of its value, then what would happen to his angular velocity? Well, if this guy went down to a factor of 1/2, then this guy has got to go up by a factor of 2. So if you consider me in these masses, I have an angular momentum of 0, and no matter what I do, I cannot change it to be anything other than 0. Now, if I go ahead and get myself spinning with a large rotational mass, and I pull those into a small rotational mass, my angular speed has to go up correspondingly. Haha.